Organic Chemistry Lecture 7, Carboxylic Acids. Before we begin this lecture, take note that this is probably going to be one of our lengthier lectures in the series. This is because carboxylic acids are a very popular topic on the MCAT. Starting with the fundamentals, carboxylic acids contain both a carbonyl and a hydroxyl group on the same carbon. Because of this, they're always going to be terminal groups. A general structure of a carboxylic acid is going to look like this. The nomenclature is like with the other ones. You replace the E ending on the parent alkane with an oic acid ending. There are dicarboxylic acid groups as well. Put simply, a dicarboxylic acid is just a compound that has a carboxylic acid on both ends. This is noted by the ending dioic acid. Remember that since both of these have to be terminal groups, we don't have to number where they are. Just by being called a carboxylic acid, it is noted that the carboxylic acid functional group is going to be terminal. Physical properties of carboxylic acids are largely why they are tested on the MCAT, because they exhibit a lot of very interesting traits. For starters, they're polar and can form hydrogen bonds. This is going to increase their boiling point because they can hydrogen bond with each other. They also tend to form dimers when they're in solution. In terms of acidity, hydroxyl hydrogens are very acidic. This is because of the resonance structure that happens when they're removed. If I were to draw out what this sort of resonance would look like, it would look something like this. So if I've got a carboxyl group, a carboxylic acid group, excuse me. So if I have a carboxylic acid group, this hydrogen right here is going to be acidic, and this is going to lead to the formation of a resonance structure. And the resonance is going to juggle between these two forms. Because of their ability to stabilize this negative charge, this hydrogen is going to be very acidic, thus leading to the name. They're called acids for a reason. Another factor that's going to adjust or mess with the acidity are electron donating and electron withdrawing groups. Electron withdrawing groups, as the name would suggest, draw electron density away from the hydroxyl group, increasing the acidity. Note, one group that you're going to commonly see on the MCAT is going to be NO2. Electron donating groups, as the name suggests, donate electron density to the hydroxyl group, thus decreasing the acidity. The groups that you will most commonly see on the MCAT are NH2 and OCH3. Especially when it comes to phenols, you may want to take a note of electron withdrawing and electron donating groups, because these two types of groups are also going to imply the chemistry of that compound. For the better part of the rest of this lecture, we're going to talk about the synthesis and reactions of carboxylic acids, starting with how they're made in the first place. Below is the most common reaction you're going to see on the MCAT, but take note that stronger oxidizing agents are also going to convert aldehydes into carboxylic acids as well. Nucleophilic acyl substitutions are very common reactions you'll see on the MCAT as well, especially when it comes to carboxylic acids. The mechanism is listed below, but the general thing you have to note is that the nucleophile is going to attack the carbonyl, and the byproduct of this is going to be the ejection of water. Carboxylic acid reductions are, quite simply, when there is a protonation. When this occurs, as with the other reactions, you're going to note that there is going to be a removal of one of the oxygen groups. The mechanism is listed below. Decarboxylation is simply the removal of carbons, as the name would suggest. One thing that you can note from this is that if you have a dioic acid, which is listed below, it can react with itself and separate. And as we remember from the previous lecture, there is a ketoenol tautomerization noted. Saponification, you should think of soap. This occurs when fatty acids are mixed with lye. Soap solvates nonpolar compounds in aqueous solutions because of their nonpolar tails and polar heads, and they form micelles around the nonpolar compounds. So if I have something in solution that is nonpolar, what you'll see is all of the tails are going to be associated with it, and the polar heads are going to bunch up and surround this compound. This is going to create a spherical structure around this nonpolar compound, making it able to be removed from solution. This is generally why we consider soap to be so good at cleaning things. We've covered some fundamentals of carboxylic acids. In the next part of this lecture, we're going to go over carboxylic acid derivatives. We'll start with amides. Amides have the formula RCONR2, and R2 just simply meaning functional side chain 2. You replace the oic acid ending with amide, and cyclic amides are called lactams. When you name lactams, you just replace the oic acid with lactam. And below is a basic amide formation reaction. As you can guess, this results from a nucleophilic attack and the removal of water, which is very characteristic of nucleophilic addition reactions on carboxylic acids. Esters are hybrids between carboxylic acids and an ether. The dehydration synthesis product of other carboxylic acids and derivatives will result in esters. You replace the oic acid ending with OH in these compounds, and cyclic esters are called lactones. Below is a basic condensation reaction of esters. As you can see, this is also very characteristic of a nucleophilic addition reaction, and the byproduct of this is also water. As you can see, there's a very common trend when it comes to reactions of carboxylic acids. Make sure you take a note of them, because on the MCAT you will see a lot of these reactions, and most of them are going to be very similar. The Fischer esterification also results in the expulsion of water, and it results from the attack of an alcohol. The hydroxyl group on the alcohol is going to act as a nucleophile and attach itself to the carboxylic acid carbon. The result is a protonation of the existing hydroxyl group and its respective ejection. Anhydrides are simply compounds that have two carbonyls and an oxygen in between their chain. You replace the oic acid ending with anhydride, and the general formula is listed below. Here's a basic synthesis. If you heat up carboxylic acids for long enough, eventually you are just going to form anhydrides naturally, along with the expulsion of water. Below is a carboxylic acid condensation reaction. Again, if you put carboxylic acids in solution and heat it up for long enough, you are going to get a reaction such as this. If you remember from the previous slide, we actually showed a reaction like this, but here's the more proper mechanism. An interesting thing about carboxylic acids, especially dioic acids, is that within molecular structures, so intramolecular structures, you can form anhydrides with the addition of heat. This is going to lead to the closing of rings, for example, what you see below. Again, the byproduct of this is going to be water. In terms of reactivity principles of derivatives, there is a relative reactivity. Here is the tiering of that. Anhydrides are more reactive than esters, which are more reactive than amides. This is a general rule that will serve you well on the test. In addition to that, there are steric effects. Steric hindrance, as you have recalled from previous lectures, impedes the reaction due to the size of the substituents. Electronic effects are based on induction and conjugation. Induction is the distribution of charge across sigma bonds, and conjugation is the presence of alternating single and double bonds. Based on the presence of these two, you're going to see differences in reactivity. And lastly, the strain in cyclic derivatives, which is based on bond angles, structure, and functional groups. This strain is also going to dictate its reactivity. If the strain is too severe, you'll likely see the ring breaking. There are three types of anhydride cleavages, and they all have the same mechanisms. The first we'll talk about is anhydride to an amide and carboxylic acid. This cleavage is propagated by the attack of an NH3, and the mechanism is listed below. When you cleave an anhydride to an ester and a carboxylic acid, this cleavage is constituted by the attack of an alcohol. And the last cleavage is simply when water is the attacking nucleophile. This creates two carboxylic acids. Transesterification as the name would suggest, is simply the adjustment of an ester. So, as you can see, if you look at the starting reagent, you have a methyl group, and in the product you have an ethyl group. They basically just switched. The mechanism is not terribly important for the test. Just note that if you see something similar to this, you're looking at a transesterification. The last subject that we're going to talk about in this lecture is the hydrolysis of amides. And the thing that's interesting about this reaction is that you're not going to see water as the byproduct, or the ejected leaving group. Instead, you're going to see water as the attacking nucleophile, with the NH3 group as the leaving group. Other than that, the reaction is very similar to the reactions that we have seen previously in this lecture. So I know this was a pretty lengthy lecture, but carboxylic acids are very important when it comes to biology and biochemistry proper. Having a good understanding of this is going to bleed over into your general sciences and biological sciences sections on the MCAT. So make sure you study hard and have a good grasp of these reactions. But take note that there are very similar trends that you will see throughout all these reactions. Please join us in the next lecture as we talk about nitrogen and phosphorus containing compounds.